Welcome to all. Today we are going to solve GATE Mechanical 2025 papers and the problems which are associated with applied mechanics and design. That is engineering mechanics, mechanics of materials, theory of machines, vibration and design of machine elements. So let us start. This is the first problem. It has been asked that the yield stress of a metal in uniaxial tension, that is SYT, yield stress in uniaxial tension is 200 MPa. According to von Mises yield criteria, the yield stress of the metal in pure shear is to be determined. We know that yield stress in shear SSY is SYT divided by root 3, that is equal to 0.577 SYT. This we have derived in our full course class. You can go through that. For full course class, please WhatsApp me in the given number in the description box. So let us put the values. You will get the value of SSY. SSY is 0.577. SYT is 200. And you will get 115.5 MPa. So let us find the options. So first option, that is option A, is the correct one. Now let us move to the next problem. A rigid circular disc. This is the rigid circular disc. Radius R, it is mentioned here, radius is R, is rolling without slipping. It is rolling without slipping on the flat surface. This is the flat surface. This is the flat surface, as shown in the figure below. The angular velocity of the disk is given and omega in radian per second, that is SI unit. The velocities in meter per second, that is also SI unit, at points O and A are to be determined. O is here, A is here. And it is also mentioned that R is in meter. So all units are in meter. So whatever velocity we will get, that will be also in meter per second, that is mentioned. Now we know that for a disk which rolls without slipping, the instantaneous center of velocity IC lies at the point of contact, which is nothing but A. So this is the IC. So at instantaneous center, where instantaneous velocity is 0. So velocity at point A is 0. But in the options, it is given in the with the vector form with unit vectors I along x direction, j along y direction. So that is velocity will be 0 I along x direction, no velocity of the instantaneous center of point A. Now what will be velocity at the center of the disk, that is O. So VO, we know that we have done several times in our full course. VO is VA plus VOA. VA is 0 and VOA will be what? Omega cross R. Omega cross R. Now here, what is omega? Omega is shown here. Direction of omega is shown here. And from right hand rule is what? That is, put your right hand like this. Put your right hand like this. If these four fingers are giving the direction of rotation, then thumb will give you the direction, the vector direction. So by these you can understand easily. That is, the omega vector is perpendicular to this plane, that is perpendicular to the screen, and inside, towards the inside of the plane, that is who is the viewer, that is opposite direction, that is minus k. So omega here, it is minus k, that is omega minus omega k cross. What is R? Sorry, what is R here? R is nothing but O to A. O to A. Omega cross R. R here, OA. Better here write down omega cross OA. What is OA? OA is R into J, because this is positive J direction, RJ. That is VO What is omega cross j? Sorry, k cross j. You know the ijk cross product rule. K into j is nothing but minus I. So this minus and this minus will be plus. So R into omega k cross j is minus I and this minus will plus. So I. So R omega I and 0 I. And you can see that the option A is the correct one. So this is the answer to the problem. Now let us move to the next problem. Here this is a truss problem. A truss structure is loaded as shown in the figure. Among the options given, which member in the truss is a zero force member? So which member is zero force member, that we have to find. This is A, this is B, this is C, this is D. So how many truss members are there? That is AD, AD, AB, AB, BD. So let me write down BD. This is BD, this is BC, this is BC and CD. So 5 members are there. Let us find which member having zero force component. Now if I take a section here, method of section, then if I draw the free body diagram, that is this is A, here F is applied, then at this point force is F AD, and here this point force is F AB. Now if I go through the equilibrium equations, that is summation of f of x is 0 and summation of f of y is 0. F is 1000. F is 1000. So you can easily find that FAB having some value. So that is FAB is not equal to 0 and FAD is also not equal to 0. Both will have some value. By these two equation we can find them. I am not going to find here because I have to calculate only which member is zero force member. Now let us come to here. Why I come to here? Because this member is perpendicular to BC and AB. Here this angle is 90 degree. Now let us draw the free body diagram at joint B. At joint B, this force is FAB. This force is FBC and this force is FBD and this is 90 degree. Now FAB, we know that this is not equal to 0. And now right now if I consider two different direction, that is this is I direction and this is J direction. If they are mutually perpendicular direction, I and J, they are both are two direction which are mutually perpendicular. Now for equilibrium we can write that summation of f of I is 0 for point B and summation of f of J is 0. If I apply this equation, that is summation of f of I 0, what we will get? F AB is F BC, and both are not equal to 0 and they both are not equal to 0. So FBC is also not equal to 0. FABB is not equal to 0. But when we apply summation of f of J is 0, what we will get? FBD is 0. BD is 0 because no other force along this direction. So as FBD is 0, that is BD is a zero force member. So this option is correct. That is BD is a zero force member. We have done this in our full course. Now let us move to the next problem.
Are you a GATE mechanical aspirant? Then you are at the right place. Join Mechanical Academy, your ultimate gateway to IITs and PSUs. Meet with our expert faculties. Their details are shared here. Both of them having more than 10 years of teaching experience for GATE. We provide video lectures, live classes, solution of previous GATE 20 years papers, study materials in well-documented book form, doubt solving, and last but not the least, test series. Your dreams course starts here at Mechanical Academy. For details, WhatsApp 8777 035 176. Please follow our YouTube channel and books. Links are provided at the description box. So, looking forward to meet you soon.
Now, here it has been asked, a metallic square plate is subjected to a uniform hydrostatic pressure. So this is a metallic square plate subjected to uniform hydrostatic pressure P. That is, when it is subjected to uniform hydrostatic pressure, that is along x direction minus P, along y direction minus P, along z direction minus P, x and y direction, two-dimensional, because it is a plate, so two-dimensional object. Sorry, all that is sigma x. So this is sigma xx and this is equal to sigma yy. Both are minus P, and shear stress tau xy is 0. Tau xy is 0 because fluid at static cannot sustain any shear stress. So this is the state of stress when it is subjected to hydrostatic stress. Choose the correct Morse circle representing the state of stress at any point in the plate from the options given below. For Morse circle, it is given normal stress is positive towards right, that is along this direction, normal stress is positive, and shear stress is positive towards upward direction as conventional way. So our stress, state of stress is sigma xx is minus P, sigma yy is minus P, and tau xy, sorry. So already I have mentioned here, let us write down once again, sigma xx is minus P, sigma yy is minus P, and tau xy is 0. Now if I draw the Morse circle, sigma n and tau, both are minus. So here it is sigma xx comma tau xy, as tau xy is 0, and sigma yy comma tau xy also at this point. So Morse circle becomes a point for hydrostatic stress. Okay, so here it will be a point. Now here it is at positive axis, so non-correct, it is not correct. Whereas option B, you can see this is minus P here, and that is the correct option. Okay, and these two are also incorrect because Morse circle becomes a point for hydrostatic stress, and this problem we have done several times in our full course. Now let us move to the next problem. A block of mass 1 kg, mass is 1 kg, connected to a spring of stiffness, so spring stiffness is 10 Newton per meter, is operating in a viscous medium, such that damping ratio or damping factor, that is zeta, is equal to the ratio of damp frequency to the natural frequency. What is natural frequency? We know that omega n, and this should be damped natural frequency, and that is omega d. So zeta is the ratio of what? Zeta is the ratio of omega d by omega n. Let me explain here physically what is this is the spring mass system. No damping is subjected here. Now say this is the same spring mass system, which is under fluid. So fluid will provide damping to the system. Natural frequency of this system when it is undamped, that is omega n, and under this fluid, the natural frequency of this system is called omega d, that is damped natural frequency. Here it is given only damped frequency, that should be damped natural frequency. Okay, so zeta is nothing but this, and we have derived, you can see that omega d is omega n root over 1 minus zeta square. That is omega d by omega n is root over 1 minus zeta square. So zeta, So zeta, what is the value of zeta? Zeta is this ratio, that is nothing but root over 1 minus zeta square. That let me square at both sides, 1 minus zeta square. That is 2 zeta square is 1. That is zeta square is 0.5. Is zeta becomes 0.7, sorry, 707 becomes 07. Okay, it has been asked to find round up to decimal place, so you can write 0.71. So this is the answer to the problem, 0.71. Now let us move to the next problem. This is another problem from vibration. The system shown in the figure below consists of a cantilever beam. This is the cantilever beam with flexural rigidity EI. EI is the flexural rigidity and negligible mass. The beam has no mass, or you can neglect that. Very small mass. A spring with constant K. This is the K constant and this is the spring. And negligible mass also. Both beam and the spring having negligible mass. And the block mass, this is the block mass M. Assuming lumped parameter model of the system, the fundamental natural frequency has to be determined. What is the omega n to the system? Before finding that, I will uh, ask you to find the stiffness of the cantilever beam. This is a cantilever beam. What is the stiffness of a cantilever beam? If this is a cantilever beam, when it is subjected to force P, it having length L and flexural rigidity EI. What is the deflection at the free end? We know that delta is PLQ 3EI. Now, what is stiffness? Stiffness is force by deflection. So KB, say B for beam, KB is P by delta. P by delta, that is nothing but 3EI by LQ. So stiffness of the cantilever beam is 3EI by LQ. This type of problem we have solved several times in our full course. Okay. Now, how to find the natural frequency? What we shall do? This is the equilibrium equation. We shall disturb the system from the equilibrium position by deflecting it by very small amount. Deflection, angular deflection is theta, angular velocity is theta dot, and angular acceleration is theta double dot. Due to that, what is the linear deflection at this point? Say beam is OA. What is linear deflection at this point? L theta. Linear deflection L theta, linear velocity L theta dot, linear acceleration L theta double dot. Now, what are the forces? What are the forces? The spring will provide a force, that is K into L into theta. K into L into theta, stiffness into deflection. So this is the spring force. What is the force due to stiffness of the beam? Due to stiffness of the beam, that is KB. KB is the beam stiffness into L theta. Now, the mass M, this block mass M, having acceleration L theta double dot along which direction? The acceleration A is L theta double dot. Now, if I want to convert this system into static equilibrium system by applying D'Alembert's principle, we have to add one inertia force, and the value of inertia force is m into acceleration, and which is opposite direction to the acceleration. That is m L theta double dot, m into A, m into acceleration. So these three are the forces, unbalanced forces, and at equilibrium they will uh, and at equilibrium what we can write, that is, if this is, say this direction is y, this is y, this is x, so at equilibrium what we can write, summation of f of y is 0. If summation of f of y is 0, then we can write ml theta double dot plus kl theta plus kbl theta is 0. Along y direction, summation of all forces are 0. By doing this, we get this, and this is the governing equation. Now we can cancel L from this equation, that is m theta double dot plus k plus kb into theta is 0. Now let us modify this equation. M theta double dot plus k plus kb by m theta is 0. Now let us compare this equation with the equation of simple harmonic motion. Simple harmonic motion, that is theta double dot plus omega n square theta is 0, where omega n is the natural frequency. By comparing this equation, this is the governing equation, and this is the simple harmonic motion. Comparing these two, what we will get, that is omega n square is k plus kb by n. Now omega n is root over k plus kb divided by m, that is root over k plus 3 ei divided by L cube. This is the value of kb, 3 ei by L cube we have determined earlier, L cube divided by m. So this is the value of natural frequency. Now let us find which option is correct. 3 ei by L cube plus k divided by m. So option A is the correct one. Okay, option A is the correct one. Now let us move to the next problem. The endurance limit of a specific grade of steel is same as its yield strength. Endurance limit is AC, which is equal to yield strength in tension, SYT. The ultimate strength, that is SUT, ultimate strength of this grade steel, the grade is not mentioned, some specific grade of the steel, is twice of its yield strength. Ultimate strength is twice of its yield strength. A component made of this steel is loaded in tension and unloaded periodically. So how the load time diagram will be? If I draw the load time diagram, say this is time, this is load. Okay, it will be like this. Periodically, that is loaded up to this, loaded up to this, say this limit is maximum limit of the load is sigma. So loaded at here, then becomes 0. Loaded to sigma and then becomes 0, and that continues periodically. So this is a fluctuating load or fluctuating stress. It is required that the component doesn't fail at least 10 to the power 6 loading cycles, and corresponding 10 to the power 6 loading corresponding limiting value of the stress is called nothing but endurance strength for the steel. We know that for SN diagram we have seen the diagram becomes like this, and this is the corresponding 10 to the power 6 cycle. Okay, now what it has been asked, as per Soderbergh law, consider the factor of safety, that is factor of safety is given is 2, and as per Soderbergh law, this is very important. Okay, the maximum applied tensile principal stress is to be determined, that is value, what is the value of sigma is to be determined. Now what is Soderbergh diagram? What is Soderbergh diagram? Let me draw it here only. I can draw it here. So this is sigma A, this is sigma A. What is sigma A? Sorry, I'm extremely sorry. I have drawn opposite. This is sigma M, mean stress, and this is amplitude of the stress. This is for fluctuating stress. What is sigma M? Sigma M is the mean stress, that is sigma max, that is sigma minimum stress is 0 divided by 2, that is sigma by 2. What is sigma A? Sigma A is the stress amplitude, that is nothing but this is the sigma A, and this is the sigma A. Sigma A is sigma minus 0, sigma max minus sigma mean by 2. That is also sigma by 2. Sorry. Both are sigma by 2 here. Both are sigma by 2. Now, what is Soderberg line? What is Soderberg line? Soderberg line is the boundary is AC and SYT. Joining these two, we'll get Soderberg line. So this is the Soderberg line. This is the Soderberg line. That is the boundary which defines that inside the boundary, that is inside this side is safe. This side is safe. Whereas here, red points, these red points are failure points. So this is the Soderberg diagram. We have to ask to find this as per Soderberg. Now, how we shall define the load line? That is, this is the loading. This is the loading on the component. How we shall define it? By defining the ratio sigma A by sigma M, which is nothing but what here? Both are sigma by 2. So 1. And that is nothing but tan of theta. Slope of the load line. That is slope of the load line. So this is the load line. This is 45 degree. Tan theta, that is 1, means theta is 45 degree. So this angle is 45 degree. I am writing here. And this is the limit of the loading. That is, Soderberg diagram says that this is the limit of the loading. Beyond that, failure takes place. Now, what is the limit of the mean stress? If I project this line to mean stress axis, it will gives here. This is the maximum value of mean stress. This is the maximum value of mean stress. And what will be the value that? If this angle is 45 degree, this will be SYT by 2. So maximum value of mean stress is this. Okay, and mean stress, let me consider mean stress, that is sigma by 2. So applied mean stress is sigma by 2. This is applied mean stress, which is equal to maximum value of mean stress, that is SYT by 2 divided by factor of safety. So what is this? This part is, this is applied mean stress. Applied loading mean stress. And what is sigma y by 2? From Soderberg diagram, we have find that this value is the maximum limit of mean stress. This is the mean stress axis. Abscissa is the mean stress axis. This is the mean stress axis, and this is the limit of the mean stress. So limit of the mean stress divided by factor of safety, which is also 2 given. So now sigma by 2 is SYT by 2 into 2, that is 4. So sigma is SYT by 2. So this is the maximum value of applied stress. Maximum value of applied stress is sigma. Here it is shown. So maximum applied tensile principal stress is sigma y by 2. Sigma y by 2. Now let us find the option. 1/4 of the endurance limit. So it is given in function of endurance limit, and at first you see that endurance limit is equal to SYT. They are given. So that is also equal to AC by 2. So half of the endurance limit. So which option gives that? This option. So option B is correct here. Now let us move to the next problem. Here, the state of stress at a point is shown in the figure given below. Under plane stress assumption, plane stress means if it is given in XY plane, that is sigma ZZ is 0. Normal to the plane, the stress value normal to the plane is 0, that is sigma Z is 0. The normal strain along thickness, that is epsilon ZZ, is to be determined for 2 decimal places. Now Young modulus is given 200 GPa and Poisson ratio is 0.27. Now let us apply generalized Hooke's law. ZZ is 1 by E zz minus mu sigma xx plus sigma yy. So let us put the value. This is very easy one. That is 1 by 200. That is in GPA. And you can see that is sigma xx. This is sigma xx is also in GPA. Sigma yy is minus this because this is compressing. And tau xy, this is also minus tau xy. So is minus 50 GPA. So all are GPA, all are in GPA, so there will be no problem. They will be cancel each other. So all are in GPA. Now let us put the value. Sigma zz is 0. So minus mu is 0.27. Sigma xx plus sigma yy, that is 350, and sigma yy minus 150. So epsilon zz is 1 by 200 minus 0.27 into 350 minus 150 is 200 minus 0.27. So this is the answer to the problem. I have solved this.
Are you a GATE mechanical aspirant? Then you are at the right place. Join Mechanical Academy, your ultimate gateway to IITs and PSUs. Meet with our expert faculties. Their details are shared here. Both of them having more than 10 years of teaching experience for GATE. We provide video lectures, live classes, solution of previous GATE 20 years papers, study materials in well-documented book form, doubt solving, and last but not the least, test series. Your dreams course starts here at Mechanical Academy. For details, WhatsApp 8777035176. Please follow our YouTube channel and books. Links are provided at the description box. So, looking forward to meet you soon.
A simply supported beam of length 1 meter, this is 1 meter, subjected to a uniformly distributed bending moment 1 Newton per meter, 1 Newton meter per meter, 1 Newton meter per meter. That is distributed bending moment, external bending moment, throughout the length as shown in given figure below. The bending moment at midpoint of the beam has to be determined here. So what to do? Let us find the reaction forces Ra and Rb. From the equations of equilibrium, Ra plus Rb is 0, there is no force. Now let us take a moment about A, that is summation of all moments about A is 0. What we will get? Rb into length, length is the 1 meter, 1 meter, it gives a moment counterclockwise sense, whereas external moment, this moment is clockwise sense. So minus, what is the total moment? 1 Newton meter per meter, and length is 1 meter, so 1 into 1, that is 1, 0. That is Rb is 1, Rb is plus 1. Then what is Ra? Ra will be minus 1 because Ra plus Rb is 0. So let me correct this. This direction will be opposite to that. So this is Ra 1. And Rb is also 1 Newton. Both are 1 Newton, but they are opposite to each other. Now, what will be the shear force diagram? Let me draw it. Or we can directly find shear force diagram will be negative. Because here reaction force is negative and there is no force on the beam. So continuously it will be constant minus 1 Newton. This is Vx. So from the diagram, using relationship, we can also find bending moment diagram. But here I am trying to draw for you. Let us take a section at any section X here. Or sorry, let us take any section here or any here. This length is X. X is more than half length of the beam. And this is X. This is X. Then what will be the free body diagram? This is 1 Newton. This is bending moment has to be determined here, and uniformly distributed bending moment, that is 1 Newton meter per meter. So let us take the moment about this point, that is mx plus 1 Newton into x. And what is the total external bonding moment? 1 Newton per meter into x meter, that is 1x, and that is opposite to that, minus 1x 0. That is mx is 0. So bending moment at the midpoint is 0. And from bending moment, from the shear force diagram that we have done several times in our full course, you can try it. That is for your task. So here bending moment is 0. This is the answer to the problem. Now let us move to the next problem. An isotropic brittle material is tested in the universal testing machine. The stress strain diagram for material shows a bilinear elastic behavior. This is one linear, this is another. So bilinear elastic behavior. As shown in the figure below, the strain energy density, that is strain energy per unit volume, has to be determined, and unit is given here. We know that strain energy per unit volume is nothing but area under stress strain diagram. This is the stress strain diagram. What is the total area? This is the first area. This is the triangle. This is the triangular area. So strain energy per unit volume, let us find, that is small u. So first find the this triangular area. What will be the this triangular area? Half, height is 100, and strain is 0.01. Then what is the area? Then let us consider, let me show it by red color. This area, this rectangular area. What is the area of this rectangular area? Plus height is 100, and what is the width? This width, that is 0.015 minus 0.01. Okay, then what is left? This small triangular area. What is that? Is that plus half? What is the height? 120 minus 100, that is 20, and width is the same of this width, that is 0.015 minus 0.01. Now let us find, this becomes 1 divided by 2, that is 0.5, plus 100 into 0.005, that is 0.5, plus 10 into 0.005, that is 1 plus 0.05, that is 1.05. Now what will be the unit? What will be the unit? That is sigma into epsilon. Sigma having unit MPa, and epsilon is unitless. So unit of this is nothing but MPa, that is meganewton divided by meter square. You can write it mega Newton into meter divided by meter cube. That is Newton into meter is joule, megajoule per meter cube. So this is the unit, and it has been mentioned the same unit, megajoule per meter cube. So the answer is 1.05. 1.05. MPa is nothing but 1.05 megajoule per meter cube. Megajoule per meter cube. So this is the answer to the problem. Now let us move to the next problem. A pair of spar gear is required to maintain velocity ratio. What is the velocity ratio? Velocity ratio is omega 1 by omega 2 is half. That is, this is the pinion, small gear. It's having more speed, so speed ratio is less than 1. The module of the gears, module is 10 mm, and addendum is also 10 mm. Operating pressure angle alpha is given 15 degree. Number of teeth on the pinion to ensure no interference or undercutting. This we have done several times in our full course. And for getting the full course, WhatsApp me in the given number in the description box. So N2, N2 minimum. 2 is 2 for pinion. And pinion must having lesser number of teeth compared to gear. So minimum number of teeth to avoid interference without undercutting. This is not slash undercutting. Uh, avoid interference without undercutting. The concept is available in our full course. This is a wrong information, not interference oblique undercutting. To avoid interference without undercutting. Okay. So let me find the expression. 2 f into lambda 1 plus lambda lambda plus 2 sine square alpha root of total this minus 1. Now you know all the significance, that is lambda is the speed ratio is nothing but half. Lambda is half here. And what is the f? F is that is addendum is a function of module. So this function is f, where here both are 10. So f is 1. Now let us put the values. You know all the values here. Minimum is 2 into 1 into half, 1 plus half, half plus 2, sine square 15 degree minus 1. Let us calculate this, nothing else more. Denominator will be, numerator will be 1, and let us find the denominator separately. You will get a value 24.35 something. Please let us vote. But the minimum number of teeth must be an integer. So this should be 25, not less than, not 24. Then it will be less than that. Then there will occur interference. So it should be more than this number. And the next integer is 25. So the answer must be 25. Okay, the answer will be 25. Let us move to the next problem. Two plates. These are two plates. Thickness 10 mm. It is given. Each are joined by a transverse fillet here. This is the transverse fillet. This is the transverse fillet. Weld on one side, and resulting structure is loaded as shown in the figure below. Loaded by 5 kilonewton load here. 5 kilonewton load. If ultimate tensile strength is, if the ultimate tensile strength is 150 MPa, and the factor of safety is 3, the minimum length of the weld required to ensure that weld doesn't fail, what should be the length of the weld? That is, if I draw the 3D view, so this should be the L, length of the weld. Now let us consider the cross section of the weld. This is the cross section of the weld. These are called what? Leg. These are called leg. T is 10 mm. This is also T. And the minimum area of the weld, we shall design it with minimum area of the weld, which is along 45 degree. This is H. So throat of the weld, throat is H. That is the along which the weld area is minimum. That is T cos 45 degree. That is 10 cos 45 degree. So minimum weld area is H into L. That is 10 cos 45 degree divided by L. Now here in the problem, the ultimate strength of the material is given. No yield strength is given. And the weld is subjected to shear, that we know. Now, what should be the yield shear strength? We know that yield shear strength, according to maximum shear stress theory, is YT. I am considering yield strength in tension is equal to ultimate strength. Considering that. That is the point. This is the discrepancy of the problem. MPa. So this is the maximum value of the shear stress. Now, so this SSY divided by factor of safety is what? Yield strength in the weld. That is what? P by H into L. That is. So from this, what we will get? SSY is 75 by 3 is P is what? 5 kilonewtons. So 5 into 10 to the power 3. H is 10 cos 45 degree into L. Now from this, using this equation, you will get the L, that value of L is around 28.28 millimeter. So this is very easy problem, but one discrepancy is ultimate strength of the material is given. If it is a brittle material, then you can call it design it along ultimate strength, but for uh, ductile materials we need uh, yield strength. Okay, so this problem is from an offset slider crank mechanism. An offset slider crank mechanism shown in the figure. This is the figure. The length of stroke of the slider is to be determined. So this problem we have solved in our full course with the help of model. There will be very good understanding. You may go through that. So R, that is length of the crank, is given 30 mm. Length of connecting rod is also given, that is 50 mm. Say this revolute pair is O2, this is A, this is B. All of we know that B will move along this axis. So this is the uh, locus of point P, and point A will move on this circle. Okay, there is limited space, so A will move on this circle. Now let us, to determine the stroke, let us first define two extreme positions of point P. Let us consider this is one extreme position of point B, that is right extreme position, and left extreme position of point B, say it is here. Okay, now what will be the position of crank and connecting rod when B at BR and B at BL? This is BL. So we know that crank and connecting rod will be collinear when B at extreme position. So this is one. Say this is the corresponding position of A, because A moves on this circle. So this is, say this is AR, this is AR, and this is BR. So this is crank. O2 AR is the crank, AR to BR is the connecting rod. Next, when it is at BL, then what will be the position? That is, further it will be collinear, but one overlap on another. So here it comes here, this is AL and BL. Now what is stroke? Stroke is BL to BR. This distance is called stroke, S. So S is what? BL BR. That is, we can write O2 BR, sorry, not O2 BR. That is, if I drop this point BR prime, drop this point BL prime, that is O2 BR prime minus O2 BR prime minus O2 BL prime. So this is stroke. Now stroke, that is O2 BR prime, is what? O2 BR cos alpha 1. Say this angle is alpha 1 and this angle is alpha 2. So minus O2 BL cosine of alpha 2. Now let us find the value of alpha 1 and alpha 2. Sine of alpha 1. Sine of alpha 1 is what? This is 10 mm, offset is 10 mm divided by O2BR. O2BR is what? R plus L. R plus L, R is 30, L is 50, that is 80. So 1 by 8. That is, from this you can find out alpha easily. Value of alpha is 7.18 degree. Similarly, you can find alpha 2. You can find alpha 2. Sine of alpha 2 is what? 10 divided by this O2BL. O2BL is 50 minus 30, 20. So 10 by 20, that is half. So alpha 2 is 30 degree. Sine of half means alpha 2 is 30 degree. So what will be the stroke? O2BR. O2BR is 50 plus 30, 80 cosine 7.18 degree minus O2BL is 20 cosine 30 degree. That is 62.049 mm. So it has been asked to find it round off to nearest integer, that is 62 mm is the answer to the problem. So with this problem we are ending here. This we have solved all those problems from applied mechanics and design of GATE 2025. Thank you for watching and please subscribe my channel to get more videos on mechanical engineering.